Okay, so it's actually pretty easy to show that for learning, for training a control function, using behavioral cloning can lead to very bad performance. So let's do a worst case analysis for the simplified case, and then try to generalize it a bit. So let's assume that we have 0, 1 loss. That is, either we take the same action as the demonstrator, that's a 0 loss, or a 1 loss if we take a different action. Okay, and you can think of that as a negative of the reward, right? So losses and rewards, we can use them interchangeably. We just need to use the negative of each other. Okay, and now let's assume that we trained our supervised model pi theta to actually have a very low loss value. So we trained it to be very accurate. So for all of the states in our demonstration set, the probability that our trained policy will take an action other than the action provided by the demonstrator is very low. It's lower than some small epsilon. Okay. So we have very low training error. Now what would happen in practice? So what is the expected loss for an entire trajectory? Okay, let's try to compute that, because we don't care about, well, a single step, we care about controlling but through a full trajectory. So we have some probability of making a mistake in the first step, right? What is that probability? Well, it's epsilon, as we said before. I mean, in the worst case, it's epsilon, right? So this is why it's smaller or equal to epsilon times, okay, now the loss, the accumulated loss from that step onwards, in the worst case, we'll get to a new state that we never seen before because we didn't follow the demonstrators. And at that point, we'll just take wrong decisions because we can make no assumptions about states that were not in our training set. Okay, so we're in a completely new region, and then we make mistakes until the end of the trajectory. So how many mistakes are that? That's t mistakes, right? I'll just remind you that for each time step, if we make a mistake, the loss is 1. We have t mistake after the first, including the first mistake. So we have, in total, all of the trajectory will be mistakes, and we have an epsilon probability of doing that, right? This is exactly if we take the first step, make mistake on the first step. So we made a mistake on the first step, we reached unknown terrain, and we continue to make mistakes until the end. Okay, but the complementary probability is that we'll actually take the correct action in the first step. So that has a probability of 1 minus epsilon. But then, again, we run into the risk, a very low probability, maybe an epsilon probability, of making t minus 1 mistake. So again, we'll diverge from the demonstrator in the second time step, and then we reach unknown terrain, and we continue to make mistake until the end of the episode. And of course, we can continue this. So what is the probability of making a mistake at the third time step, and so on. You can see that we can easily accumulate this series. And this series sums to an order of epsilon times t squared, which is actually very bad expected loss, even if epsilon is very low, right? So it's very sensitive to the length of the episode. This is something that's, well, not very good mathematically, right? At the end of the day, this is a loss that is can be considered very high. But you might say, well, we can actually, this is a bit of a strong assumption, just to say that we only fit states that are in our demonstration policy. Let's say, as Vaibhav mentioned out before, that we have as many training data that we need. So not only are we correct, we have a good error rate for all of the training set, but let's say that we have a good error rate, or that is lower than equal to epsilon, for all states that we might encounter using our demonstrator policy, right? So for the entire distribution of states drawn from our expert policy. Even if we assume that we are not only accurate on the training set, but accurate on indeed everything that we want to be accurate on, that is the entire state distribution that can be drawn by following our expert demonstration, and we have very good, we can fit that distribution very well, still we won't get a better worst case. The worst case will still be an epsilon of capital T squared. And the full derivation can be seen in this paper here. I added the citation, Rosatel 2011. So, do we never want to use behavioral cloning? As we saw, both practically, we saw it in the driving domain, and both by doing some worst case analysis, we saw that behavioral cloning is not many times doesn't have very good guarantees and might perform not very good. But still, in some situations, we still want to use behavioral cloning, specifically if we can get very diverse demonstrations. Specifically, so for our driving domain, we have a driving demo in our lab with an autonomous car, a small scaled autonomous car, and behavioral cloning works well there, right?
Given no changes to the environment.
Given that we are able to really collect demonstrations for the entire environment where we operate in. So we still use behavioral cloning for some of our outreach activities. And when we collect data for training the small autonomous vehicle, we do try to go to traverse on any parts of the track, right? We're trying to collect very diverse training set. So it might still work, specifically if you do very good data collection that can cover the entire state space. And there are some practical advantage for using behavioral cloning. Mainly, it's very simple. It's very simple to define, it's just supervised learning, and it's very simple to train. And it can be trained very efficiently because we can do it offline, just on the computer. We collected the data and we train it offline. We don't have to run our car or any robot during training. So, pretty efficient. So, as I said, there are some advantages to still using behavioral cloning, and it might work well. When do we want to use it? First of all, when one-step deviation is not too bad. When we learn a reactive behavior by the demonstrator. And when the expert trajectories cover most of the state space, the entire state space. Right? So, these two are not really relevant for the driving domain, maybe. But as I said before, so when we do the demo, we try to cover the entire state space when we collect data. Right? And again, then we can use behavioral cloning also for a demo. In an outreach activity, we can do it very quickly. Right? Unlike reinforcement learning that might take time. Disadvantages. The distribution mismatches between training and testing might cause a collapse in performance. And at the end of the day, we don't perform long-term planning, right? We just rely on minimize one-step deviation, which might be a problem. In some cases, specifically, if we have a demonstrator that is doing long-term planning, and then we're just trying to imitate its one-step deviation, that might miss the point. So situations where you shouldn't use behavioral clonings are those where one-step deviation can lead to catastrophic errors, and when you are optimizing long-term objectives, well, at least without having a stronger model.